Hello all. In this video we will look at the proof of convergence for the accelerated gradient descent for the strongly convex functions. We begin with a quick overview. Recall that we are considering the unconstrained problem x star is equal to argmin over x f of x. The accelerated gradient descent for this case takes the form dt equal to gamma times xt minus 1 and xt plus 1 equal to t of xt plus dt, which is xt plus dt plus gt, where the operator t is defined as t of x equal to x minus 1 over L gradient f of x. Recall that we set eta equal to 1 over L throughout, and gt equal to minus 1 over L gradient of f of xt plus dt. The objective function f is L smooth and mu strongly convex. We will use the momentum parameter gamma equal to square root of L minus square root of mu divided by square root of L plus square root of mu, and eta equal to 1 over L. The result is that the oracle complexity of the accelerated gradient descent is order of square root kappa times log of bf plus b divided by epsilon, where kappa is equal to L over mu. The proof for this case starts in a similar fashion, but here notice that we have kept the momentum parameter constant. In fact, the goal here will be to obtain a contraction bound instead of a telescopic sum. We start in the same way as in the convex case, but here we will use the quadratic lower bound instead of the first order convexity condition to obtain the two one-step inequalities. Recall that we denote the optimality gap by delta t. Recall also that we had used the quadratic upper bound to obtain that f of xt plus 1 is less than equal to f of xt plus dt minus 1 over 2l norm square of gradient f of xt plus dt, which can be written as f of xt plus dt minus L by 2 norm square of gt. Now for the first inequality, we use the quadratic lower bound at xt and then rearrange so as to obtain delta t plus 1 is less than equal to delta t minus L by 2 norm square of gt plus 2 times inner product of gt comma dt minus mu by 2 norm square of dt. And for the second one, we use the quadratic lower bound at x star and rearrange so as to get delta t plus 1 is less than equal to minus L by 2 norm square of gt plus 2 times inner product of gt comma xt plus dt minus x star minus mu by 2 norm square of dt plus xt minus x star. As in the convex case, we can combine these inequalities to obtain delta t plus 1 minus 1 minus beta delta t is less than equal to minus L by 2 norm square of gt minus L times inner product of gt comma dt plus beta times xt minus x star minus mu times 1 minus beta by 2 norm square of dt minus mu times beta by 2 norm square of dt plus xt minus x star. As earlier, we will use the formula that norm square of u plus 2 times inner product of u comma v can be written as u plus v norm square minus norm square of v, which yields that the right hand side can be written as L by 2 norm square of dt plus beta times xt minus x star minus L by 2 norm square of gt plus dt plus beta times xt minus x star minus mu times 1 minus beta by 2 norm square of dt minus mu times beta by 2 norm square of dt plus xt minus x star. For the second term, observe that dt plus 1 is equal to gamma times xt plus 1 minus xt, which is equal to gamma times dt plus gt. So in the second term, gt plus dt plus beta times xt minus x star can be written as 1 minus beta by gamma into dt plus 1 plus beta times xt plus 1 minus x star. So substituting this and rearranging, we obtain that delta t plus 1 plus L by 2 times norm square of 1 minus beta by gamma into dt plus 1 plus beta times xt plus 1 minus x star is less than equal to 1 minus beta times delta t plus L by 2 times norm square of dt plus beta times xt minus x star minus mu times 1 minus beta by 2 norm square of dt minus mu beta by 2 norm square of dt plus xt minus x star. We need to arrange this so that we can get a contraction bound for the terms on the left. That is, we need to get an inequality which is of the form that delta t plus 1 is less than equal to 1 minus beta times delta t. To get such a contraction bound, let us rearrange the inequality as delta t plus 1 plus L by 2 norm square of 1 minus beta by gamma into dt plus 1 plus beta times xt plus 1 minus x star is less than equal to 1 minus beta times delta t plus L by 2 norm square of 1 minus beta by gamma dt plus beta times xt minus x star plus omega t, where omega t is equal to minus 1 minus beta L by 2 norm square of 1 minus beta by gamma dt plus beta times xt minus x star plus L by 2 norm square of dt plus beta times xt minus x star minus mu times 1 minus beta by 2 norm square of dt minus mu beta by 2 norm square of dt plus xt minus x star. So here we have added and subtracted the required terms so as to get it in the form of a contraction bound and put everything in omega t. So we can see that we have the required contraction bound if we can ensure that omega t is less than equal to 0. So we are free to choose both gamma and beta in order to ensure this. But if omega t is less than equal to 0, we will be able to drop it from the right hand side. Let us multiply both sides by 2 by L and then expand the right hand side so as to get 2 by L times omega t is equal to minus 1 minus beta norm square of 1 minus beta by gamma into dt plus beta times xt minus x star plus norm square of dt plus beta times xt minus x star minus rho times 1 minus beta norm square of dt minus rho times beta times norm square of dt plus xt minus x star. So this whole quantity should be non-positive. Here we have set rho equal to mu by L for brevity. So the right hand side can be written as minus of 1 minus beta cube by gamma square plus 1 minus rho into norm square of dt plus rho times beta square minus rho times norm square of xt minus x star plus 2 beta times minus 1 minus beta square by gamma plus 1 minus rho times inner product of dt comma xt minus x star. So we have expanded the quadratic form. In order to make this expression non-positive, we can choose the parameters. So first we choose the parameters so as to ensure that the cross term vanishes. So we get that gamma equal to 1 minus beta square by 1 minus rho, which makes the first term 1 minus rho by 1 minus beta into rho minus beta. So we can see that if we set beta equal to square root rho, the entire term becomes negative because square root rho is always greater than equal to rho. This implies that gamma equal to 1 minus square root rho divided by 1 plus square root rho. So finally we get the required contraction bound, which is that delta t plus 1 plus half of square root L plus square root mu times dt plus 1 plus square root mu times xt plus 1 minus x star norm square less than equal to 1 minus square root of mu by L times delta t plus half of norm square of square root L plus square root mu into dt plus square root mu into xt minus x star. Note that for t equal to 1, we can start with d1 equal to 0. So applying this inequality recursively, we get that delta t plus 1 plus half of square root L plus square root mu into dt plus 1 plus square root mu xt plus 1 minus x star is less than equal to 1 minus square root of mu by L raised to the power t times delta t plus half of norm square of x1 minus x star, which is less than equal to 1 minus square root of mu by L raised to the power t times bf plus b by 2. So if we equate the right hand side to epsilon, we can get the required oracle complexity as order of square root of L by mu times log of bf plus b divided by epsilon. This concludes both our proofs for the accelerated gradient descent. The accelerated proximal gradient descent can be used to solve the composite problem x star equal to r min over x capital F of x, which is f of x plus h of x. Here f is convex and smooth, but h is convex and proximable. The proximal variant can be developed along similar lines and is written as dt equal to gamma t times xt minus 1 and xt plus 1 equal to prox with respect to eta h of xt plus dt minus eta times gradient of f of xt plus dt. The algorithm was first proposed in the context where h was L1 norm and was referred to as fast iterative shrinkage and thresholding algorithm or FISTA. Here we do not need to look at the full proof, but only at the derivation of the two one-step inequalities. So here we need to redefine gt using the gradient mapping. So gt is equal to prox with respect to eta h of xt plus dt minus 1 over L gradient f of xt plus dt minus xt minus dt. Recall that the proximal theorem said that for every x and y, the inner product of x minus prox with respect to eta h of x, comma y minus prox with respect to eta h of x is less than equal to eta times h of y minus eta times h of prox with respect to eta h of x. So applying that inequality here by replacing x with xt plus dt minus 1 over L gradient f of xt plus dt and prox eta h with respect to x, where eta is 1 over L with xt plus 1, we obtain that inner product of xt minus xt plus 1 plus dt minus 1 over L gradient of f at xt plus dt, comma y minus xt plus 1 is less than equal to 1 over L h of y minus 1 over L h of xt plus 1. So therefore we obtain that inner product of L of gt plus gradient f of xt plus dt, comma xt plus 1 minus y is less than equal to h of y minus h of xt plus 1. So this is the key inequality required for this case. The two one-step inequalities that we want to get will follow from this inequality by setting y equal to either xt or x star. So now let us look at the two fundamental inequalities. We begin with using the quadratic upper bound and convexity, which yields that f of xt plus 1 is less than equal to f of xt plus dt plus inner product of gradient f of xt plus dt, comma gt plus L by 2 norm square of gt. For the first inequality, we use the convexity condition at xt to get that the right hand side is less than equal to f of xt plus inner product of gradient f of xt plus dt, comma dt plus inner product of gradient f of xt plus dt, comma gt plus L by 2 norm square of gt. So now we can add the inequality on the previous page for y equal to xt to get delta t plus 1 is less than equal to delta t minus L by 2 norm square of gt plus 2 times inner product of gt comma dt. Likewise, the second inequality can be obtained by using convexity as well as the inequality for y equal to x star to get that delta t plus 1 minus L by 2 norm square of gt plus 2 times inner product of gt comma dt plus xt minus x star. The rest of the steps are exactly the same because we have now obtained the same form of the two inequalities. So we are now done with the telescopic sum based proof of the accelerated gradient method. It is remarked that we can similarly develop proofs for the mirror descent and other variants. The proof approach presented here is also practical as long as you know the form of the algorithm. So its parameter can be obtained by using this approach. So that is all for this video. In the next video, we will look at another way of proving the accelerated gradient method, which is using the estimate sequences.